A review video to go over the topic of enthalpy in the context of phase transitions. Phase transitions can be a little tricky because there's some other things going on that we haven't really dealt with yet, but it also has some conceptual parts that bothers folks, and that's really true of a lot of the topics we cover in second semester chemistry. In first semester, it's kind of nice because everything is either math or it's concepts, and in second semester, the math and the concepts are more closely intertwined with each other. So there's a lot going on here that can trip people up. So let's take a look first at the conceptual part. So let's imagine that we're thinking about water boiling, and I've drawn a picture of water over here in the liquid state. The molecules are relatively close together, and then over here on the product side, I've drawn water in the gaseous state where the molecules are much more separated. So remember from first semester that water molecules are attracted to one another using an intermolecular force that involves an O to an H to an O, which is known as the hydrogen bond. Okay? So there are hydrogen bonds that are the attractive force in between each of these molecules, right? So each of these little dashed lines here is a hydrogen bond, right? So when we go from the liquid state to the gaseous state, what we're really doing is we're pulling the molecules apart, which is what we call breaking a bond, right? So we are breaking the hydrogen bonds by doing that. And remember from earlier in the semester, that means we have to put energy in. If we're putting energy in, that is an endothermic process, right? So the delta H of this process is going to be greater than 0. In other words, it's going to be positive. And I don't care which of these two notations you use. That's not true. I'd prefer you use this top notation here. But if the greater than less than signs bother you, in your own head, if you think of it that way, that's fine. As long as you understand that energy is being absorbed by the system to boil the water because the hydrogen bonds are being broken. That should make sense from the standpoint of if you think about boiling water on your stove is putting heat into the water, and eventually that will make it boil. Now, the reverse process of this is what I've drawn here below. We're going from gaseous water to liquid water, and if boiling it breaks bonds, then condensing water, the opposite, is going to form bonds, right? So we're going to get hydrogen bonds that are going to form between the molecules, and that's going to release energy, right? So this process is going to be exothermic. And this really bugs people because it doesn't quite square up with our kind of intuition on this, but it really is an exothermic reaction, all right? So as water condenses, it really does release heat, all right? This is important in things like clouds because they release their heat. The water molecules release their heat as they condense into clouds, and under certain atmospheric conditions, that can lead to all kinds of crazy things happening. Things like hurricanes get their energy from water condensation, okay? But it just doesn't seem quite right. So I always think of it from the bond breaking standpoint, which is up here at the top, and then the opposite of that has to be releasing heat, okay? All right, so that's the conceptual end of this. In general, if you're going from, and I've given myself no space here. In general, if you're going from a solid to a liquid or a liquid to a gas, that process is going to be endothermic. And if you're going from the other direction, gas going to liquid or liquid going to solid, that's going to be exothermic. All right? So it's important to kind of have those straight in your head. All right. Now, this is where the math comes in. So let's imagine we wanted to know how much heat do we need to boil 64 grams of water if that water is initially at 25. And you may or may not do this experiment in lab where you measure the temperature of water as you heat it up, and you'll notice that if you put a beaker of water on a hot plate or something, the temperature will gradually rise. If you don't change the setting on the hot plate, that rise will be more or less linear, all right? But you'll get to a point somewhere around, say 100 Celsius, where the temperature of the water will stop changing. And at that point, you'll see bubbles forming spontaneously within the liquid, and the liquid will be boiling. It'll be changing into a gas, all right? And so at the boiling point, what happens is that the temperature is no longer changing. It flattens out. But the heat that you're still pumping into it from your hot plate is being used to convert the water from liquid to gas. In other words, breaking those hydrogen bonds we were just talking about, okay? So this takes solving this problem, this quantitative problem actually requires 2 steps, all right? So the first step is going to be on this linear upward part, we're going to use our old friend Q equals Cm delta T. So let's just do that part real fast, okay? So what we're doing is we're going from, we've got to raise the temperature from 25 to 100, okay? That's the first step, all right? So we're going to do Q equals Cm delta T, and the heat capacity of liquid water is 4.18 joules per gram degree Celsius. We have 64 grams. I don't know where that number came from. And we have a final temperature of 100 minus the initial temperature of 25. I'm going to add a significant digit in here. Don't mind me. Okay, so that's going to be 4.18 joules per gram degree Celsius, 64 grams, 75 degrees C in change temperature, okay? All right, we plug that through our calculator. Or we try to. Okay, that gives us an answer of about 20,000, where are we on sig figs 3? So there we go, because grams and Celsius cancel out. We're left in joules, all right? So that's 20,000 joules. I'm going to go ahead and flip that into kilojoules just because I know where this problem's going. It's a little easier to deal with, okay? So that's the first part of it. That's this part of it where we've raised the temperature from 25 to 100, right? Now we've got to calculate this heat in here from where we're boiling it. The way we do that is we use a value that is known as the enthalpy of vaporization, okay? So the delta H of vaporization is a set number. It is, because it's in kilojoules per mole, it's 40.7 kilojoules per mole, and we're going to use that to do this calculation for the boiling. Just as an aside, we're not doing it here, but I want to mention that another important number is called the delta H of fusion, which I just hate. Fusion is an old-timey word for melting in chemistry, and it's stuck around in this context only. No one else calls melting fusion except in this one context. Okay, so if you're trying to do a problem using where you're melting ice into liquid water, you're going to use the delta H of fusion, and it's this number over here. Again, we're not doing it in this problem, but I just wanted to mention that because that will come up at some point. Okay, now how do you actually use this number? It's not just a set value, okay, because it is per mole. So the best way to do that, you can use delta H equals Q over N. If you'd like to do it that way, you're welcome to. I find that to be really messy. So the way I like to do it is I like to treat this all as a conversion factor problem. So I do 64.0 grams of water. And then I know there are 18.02 grams of water in 1 mole of water. And because I have the enthalpy of vaporization in front of me, I'm going to get rid of this, give myself some space here. I know that 1 mole of water requires 40.7 kilojoules to boil. All right, and that's just expressing that delta H of vaporization as a conversion factor. Okay, so we've done this a number of times first semester with other things, and it's just a handy way to get around having to do algebra and stuff. Okay, all right, so we're now going to plug this into the calculator. Times 40.7. Oops, I made an entry mistake there. Okay, I think I got it right now. Okay, and that's going to give us 145 kilojoules, because grams cancel and moles cancel. We're left with kilojoules. All right, so now the original question, said how much heat is needed to do all of this, right? So you boil that water off initially at 25. So we've now used the delta H of vaporization to do this, the boiling part here. So how do we get the amount of heat to do the whole thing? Well, we just add them together, okay? So we're just gonna add up the 20.1 kilojoules to raise it from 25 to 100, and then we're gonna add the 145 to boil it. And that is going to be 165 kilojoules. So that's the total to make that all happen, the whole process, both the heating from 25 to 100 and then the boiling, okay? All right, here's a practice problem for you. Go ahead and pause the video, grab a pencil, paper, and a calculator, and try to work the problem. Okay, here we go. So I've made this a little trickier because there's some unit things going on. So, la-di-da. I'm going to go ahead and flip this immediately into 1,000 grams, and just keep in mind that I've got 3 significant digits that I'm working with, okay? So the first part is going from 20 to 100, and I actually like to keep track on my paper of what step I'm doing, because sometimes, like I mentioned earlier, you might have to start with ice, and then you're going to add 2 more steps because you got to raise the ice up to 0, and then you got to melt the ice. So these can get pretty hairy, so I always like to, off to the side, keep track of what I'm doing. So because I'm raising the temperature, I'm going to use Q equals Cm delta T. Okay. By the way, the reason we can't use this equation during a phase transition, like when it's boiling, is because there's no delta T, right? The delta T is 0, so it doesn't make any sense whatsoever. So this is only for when you have a temperature that's changing, right? All right, so we got that, and we've got 1,000 grams, and we've got a delta T. I'm going to do this in my head. It's 100 minus 20, right? So it's just 80. If you do this one as an experiment in lab, sometimes the boiling point of water isn't 100 degrees Celsius that day because of atmospheric reasons, and so it's easier on paper to do these than it is sometimes in the lab, so just keep that in mind. That's that many joules, and as usual, I'm going to jump that into kilojoules. And now I'm going to do the second part of this, which is the boiling point. The boiling part, I keep saying point, the boiling part of this. So I'm going to take my 1,000 grams, which again, in the back of my head, I'm remembering that that has 3 significant digits, even though I don't have it written that way. Going to moles of water. And then I have 1 mole of water requires 40.7 kilojoules to boil. Okay, so I have 1,000 times 4.18, which I could have done that in my head, times 40.7. And that's going to come out to 170 some odd thousand kilojoules, right? So it's a lot because you're the previous example we did 64 grams, right? Which is not a lot. 64 grams is like 4 tablespoons of water. Okay, so it's not a quarter of a cup of water, not very much. Okay, now we're really dealing with real amounts of water. Okay, and notice here that the raising the temperature of this is so minuscule within the oh wait, I've made a math error here. I knew something wasn't right. Sorry guys. I multiplied when I divided. I'm glad I caught that because I would have gotten a million emails about this. Okay, let's try this again. This is 2,260. There we go. I know some of you are breathing a sigh of relief. Sorry about that. Okay, so we're going to add to that the 33 kilojoules from part 1, and because of significant digit rules, that's going to be 2290 kilojoules. All right. Okay, y'all. So The first part of this is getting it kind of straight in your head about whether which phase transitions are endothermic. Remember, if we're going solid to liquid to gas, that's endothermic because we're overcoming attractive forces. If we're going the opposite way, gas to liquid to solid, we're forming those forces, so that's going to release energy. It's going to be exothermic. And then in terms of calculations, a lot of it is we already know because we already know how to do this Q equals Cm delta T bit. The only new part today for the actual transition at the boiling or freezing point is this business about using the delta H of vaporization to do that. Okay? All right. Please leave any questions in the comments or get in touch. Thanks for watching.